with a C1 times x to the m plus C2 times x to the negative m. Is that better?
Yeah.
Guys, I've got a half hour left. I want to do something very light. It's kind of fun. I'm getting tired of looking at what I'm writing. Can we just take a 2-minute break? I can sneak off, get some decent pens.
Use the bathroom. This test is not going to be fun. There's too many methods that I don't really understand. Yeah, it's going to suck. I feel like if I took it today, I would have just swallowed it. I'm still, you guys, I'm still doing 6-3 homework. We're already up to 6-8.
Yeah, I was just
Every single one they seem to solve using, what is that? Whatever the...
I got 6-5.
No, that's part of the serum because you taste that.
Peanut butter banana.
Yeah, that's what they were doing in the search manuals for one of these. I think it was...
Oh, really?
Might have been 6-8, but like every single one. Yeah, it was 6-8. Every single
Nice, dude.
wasabi. Yeah, well, fake wasabi. I heard the real wasabi come out of it.
That's just a different type of horseradish.
Oh, really?
Japan's got a few different weird root vegetables.
Brother Tommy. Since he got pulled it in, head roll.
You gotta have the right amount of stuff. Too much.
That's all I know. I have one question.
Yes.
Since you're waiting. So steady state, does that have to do with the diodes that you're talking about? Yeah. Is that any different? Like, you know how you're like steady state diodes?
Solid state.
Solid state. Never mind.
So where does the phrase solid state come from?
Instead of using vacuum tube.
Exactly. So when we stopped using vacuum tube diodes, or vacuum tubes period, using transistors instead, I'm not sure the origin of the phrase, but we started referring to such electronic systems as solid state systems. Of course, nowadays we don't use transistors, but we use chips instead.
Oh, yeah.
Oh, okay.
Computer science majors.
It's kind of funny because, a lot of people in the music industry today have gone back to tubes. They like the sound so much better. But I remember in the 80s, this sounds so funny now. Oh, gosh, I can't remember the names. Lenny Kravitz? He said he was so unhappy with the modern chips that he decided to go retro. And he recorded a whole album using sound systems that were transistorized. Oh, do you guys get it?
Yeah.
Because nowadays we go much further back.
Yeah.
So you guys, let me play a little bit. Nothing serious, nothing deep. I got a population of robins, I got a population of worms. Do you think the robins are going to be happy that worms are around?
Yes.
Yeah, I think they will be. By the way, with my discussion today, can I just assume any concept on the board are positive? And since the robins are happy there's worms around, I think the rate at which the population changes is going to be in the positive direction. Times how many worms are around. Do you think the worms are happy there's robins around?
No.
Probably not.
Probably not. So I think in terms of the robin population, there's going to be a detrimental relationship. In that being the case, I think this is a system of two differential equations, particularly when it comes to a population model like this. And I think if I were to talk about the rate at which the robin population is changing with respect to population of worms, just because I can. So I want to discuss the interaction between the two populations. I think I can think of this as DRDT times wasn't that the same thing as DRDT over DWDT? Or shall I say, isn't that the same thing as, I have no clue, what do I have on the board? Is that a KW over a negative CR? And you guys, I just make up letters out of thin air. How about if we let K be equal to 9 and R be equal to 4? I think it simply tells me that the rate at which the robin population is changing, well, excuse me, the rate at which the robin population is changing with respect to the population of worms is simply, is that a negative 9/4? W over R. Oh, shoot. That's a differential equation. And this is a differential equation for us. So we can solve this DE. We really can. I know we can.
All right, separate it.
Separation of variables.
Yeah.
So that could be a 4 integral of R with respect to R equals a negative 9 the integral of W with respect to W. I've got my coefficient straight, don't I? And anti-differentiating. Maybe bring things to one side. What's that equation look like? What's that equation look like in the RW plane? It's just an ellipse. Well, assuming C is positive, but like I said, assume all my constants are positive. And here's my W axis. Here's my R axis. Where's the center of this ellipse? The origin. Let me not be careful. Let me not be careful with my unitization. Here's an ellipse. Centered about the origin. Now, I know technically speaking, you guys, this mathematical model is so off. It's horribly off in the sense that I'm not going to have any negative values for W, nor am I going to have negative values for R. But if you could just imagine this shifted over into the first octave. I think the relationships in this picture are pretty darn interesting. Because check out what happens as the population's right here. Then I think as a robin population increases, I got to follow this curve. I have to follow this trajectory. And when the robin population increases from 0 to something, notice how the worm population is decreasing. And the greater the R value is, the lower the W value is. Now, assuming we can have so many robins that the population of worms becomes extinct, excuse me. Well, imagine there's something there. Then I think there's so few worms, the robin population is going to be decimated until it's down to 0. Now, I think at that point, the worm population is going to increase, which means eventually the robin population is going to increase as well. Although, again, my picture should be shifted over there. At least it shows a relationship. All right, you guys, that was too hokey. Let me fix it. Well, no, I meant to do that. But now let me slowly elevate my level of complexity.
Well, you said this demonstrates the relationship between the two, but it doesn't accurately represent, like, it doesn't accurately represent populations of robins and worms?
I think for 2 reasons. Number one, pictorially, you know I'm really off because this picture shows I got negative R and W values. Number 2, I think it's a little off because I never took into consideration the effect the robin population has on the change in the population for robins. Did you guys see my point? So let me now modify my system DE. By the way, outside the math class door, this is what we do all the time. We just say, make some assumptions, we realize, oh, we're off somehow. So we come back to our DEs and we modify them to be more realistic. Now, let me modify. I think, forget about worms. This is, at least initially, a decent mathematical representation for the robin population. And forget about robins. I think this is a decent mathematical model for the worm population. Yeah, I should consider this. I won't yet. I do, however, think that if I'm gonna interchange, or excuse me, have these two populations mixed, then I think the rate at which the Robinson population is changing should take that into consideration. As a matter of fact, with the presence of worms, I think the robin population is at an advantage. And I think its rate of growth will increase. And I think it's going to increase in such a way that it's proportional to, as a constant times, proportional to the number of interactions between them. You guys, that may be hard to quantify, but I think the number of interactions between those two populations could also be interpreted as proportional to the product of the members of the population for both of those. So I can think of this as C times W times R. Now, I think the worm population is being affected by their interactions as well. I just think it's going to be a negative effect. Are you guys with me? Now, I got to confess, when you take a peek at the system DEs, this is one I'm going to have a really hard time with because it's not a linear system. So if you guys don't mind, even though this is more realistic, just so I can actually run with this and talk about things, can I come in and think of this factor as just simply a W, and this factor just simply as an R? I just try to twist this DE to be one that's more linear. And if you guys allow it and make up some numbers out of thin air, how about A being equal to, I don't know, how about 1? And B being equal to 2. And C being equal to 3. And how about D being equal to 4? Again, I don't care what they are, I'm just making fun. Then I think this is system DEs that I can solve. As a matter of fact, if I were to come in and actually just give them slightly different names, for example, let R be x1, let W be x2. I think the DE looks like this. And the second one looks like this. And I want to solve this DE. Well, I misspoke everybody. I want to solve the system DEs. Do you guys think we can use map D?
A matrix.
What's that?
I was gonna say we can make a matrix, but you can just
You could, or you just use substitution
I like that. Well, maybe not use substitution, maybe just elimination.
or elimination.
Because I think my first equation says this. D of out of x1 equals x1 plus 3x3. X2, excuse me. Second equation says this. But doesn't the first equation basically say this? And doesn't my second equation basically say this? Remember, we said we're going to use map D. So both multiplying both sides of the first equation by 4 and multiplying both sides, if I can say it this way, by D minus 1, or shall I say differentially operating with D minus 1 on both sides of the second equation, I get this. Oh, but shoot, now when I subtract the first equation from the second, like a map D, I completely eliminate the variable x1. And I think I'm merely left with a d squared minus 3d. Is that a plus 14? Acting on x2 being set equal to 0? Which means, of course, that my solutions are going to be Yeah, you use a quadratic formula. Let's use a quadratic formula.
Well,
So maybe a C1 times e to the, man, do I feel alone again? 3 halves times t times the cosine of,
you should just do the quadratic formula in your head.
all right,
I
all
mean,
right.
come
I got
on.
r squared minus 3r plus 14. Doesn't that tell me that r is equal to negative b? Cheapers. Now I'm so flustered I can't write. Plus or minus square root of b squared minus 4ac. All over 2a. But that's simply going to give me my, oh, thank you. You just showed me that I made a mistake. Well, that's embarrassing. All right, now I can't tell my math b. It's positive, negative, positive. Ay, ay, ay. Does that give me 1/2? Plus or minus, I can't clean it up. Root 47 over 6.
It should be 2. It should be 2. Divided by 6 or something.
Oh, I did have it right then. See, it's better if I took my head. I don't make mistakes. Jeepers, jeepers, jeepers. So, I think now my solutions clearly are the following. That times the cosine of my root 47 over 2 times t plus my c2 e to that power times the sine of root 47 over 2 times t. I get a mathematical model. Yes.
From C2, what is that a 3 divided by 2 or is that 3
Yes, it
divided
is.
by? Okay.
Do you guys think you can relax? Can you just let me run them up for a minute? On the very left-hand board, if I were now to solve for the function x1, by the way, as a function in time t, this is x of 2 of t. If I were to solve for x of 1, you guys take a peek at what's inside this big black box. You relax, you let me do all the work. I want to find a solution for x of 1, so I'm going to dive in here. And on the first equation, I'm going to eliminate the x2. So I'll differentially operate with d minus 2 in the first equation. And if I do, I think I get this. And my second term is going to be minus 3. D minus 2 times x over epsilon plus 2. Now I think for the second equation, I'm going to multiply both sides by positive 3, but that's going to give me 12x1. Plus 3d minus 2. x2. And when I add these two equations together, I think the x2 terms are completely eliminated. I'm merely left with d squared minus 3d. Is that a plus 14? Well, you guys, this is the same quadratic equation I had before, isn't it? And so am I not simply going to have c1 e to the 3 halves t cosine of root 47t plus c2? So you guys, it's a common mistake I see. I've done something really horribly wrong. What is it? You guys, it's more of a philosophical question. Sorry if I can't enunciate today. I've done something really, really wrong. What is it? Mike?
Wait, you forgot a 2 in the denominator on the second term, right?
Where?
We just put 3 over 2.
Oh, sorry, I'm just writing so fast.
Okay.
I think, because you used C1 and C2.
That was
there,
perfect. Did you guys see his point?
Yeah.
You know, when I write down these solutions, I blindly put down these two solutions and look at them in combination. It's not the case that these coefficients are the same as those.
Oh yeah.
And I think that's where the grammatical error is. So to fix it,
Just call it U.
call it this.
C4, C3.
And I don't want you, this time I haven't done anything wrong. I don't want to do this because I want to relate it back to C1 and C2. I'm sorry, you guys, everybody's trying to contact me at once. So I think on the left-hand board, I'm going to give up. Don't look at any of this garbage. I think
So-
instead, yes.
Well, just wouldn't it look nicer if you just kind of maintain continuity? So you do
Thank
the
you.
C3 first and then the C4?
Oh, if you insist.
Yeah.
I think a better way to maintain continuity is see if I can come up with a solution for x1 that actually uses those coefficients C1 and C2.
Okay.
I think that's even better, and there's a way to do it. I've already got x2, and I want to come up with x1. So take a peek at this relationship. If I've already got x of 2, I can find x1, and by the way, when I put x2 in here and here, I've got the coefficients C1 and C2. So you allow me. If you take a peek at that circled equation, it basically tells me that the derivative of x of 2, you guys, I don't really remember the solution, was it C1 e to the 3/2 t times the cosine of, I think, root 47 over 2 times t, plus C2 times the same thing but with a sign. This is going to be equal to negative 4x1 plus my 2x2. Did you guys see I put the t downstairs again? Jeepers. So you guys, I want a yes or no answer. Is differentiation relatively easy? Yeah, I just use a product rule, you can differentiate. And then I can bring all the terms involving C1 and C2s on one side. That gives me negative 4x1 over here. And now I can divide both sides by negative 4, and I get x of 1 completely isolated, having expressions on the left-hand side solely in terms of its coefficients C1 and C2. I've maintained that consistency. Do you mind if I don't go through the differentiation process? Well, you guys, there was my ability to actually solve a system with ease, use my math D skills and differential operators. So you can use the technique now as well. Well, you guys, I don't like my example. My example is too nice in the sense that it was a homogeneous system. What if it wasn't? Oh, you guys, I know I have an example. I made one up. How about something like x1 prime being equal to x1 plus 3x2 plus t, and then an x2 prime being equal to x1 minus x2 plus t squared. Now, if I were to rewrite this system of DEs using differential operators, you guys help me with this. Is that going to give me a d minus 1, x1, minus 3x2 being equal to t. And then my negative x of 1 plus my d plus 1 times x of 2 being equal to t squared.